Welcome everyone to our usual weekly high-energy astrophysics seminars. Today we have the pleasure to have with us Ofer Cohen. Most of you, Ofer needs a little introduction for most of you, since he has been here for a number of years, just before he got his position in Unix Lowlands. So Ofer did his bachelor and master studies in Tel Aviv University. And then he took his PhD in space and planetary physics from the University of Michigan. And then he was here for a number of years. His topics of research are planetary science, heliophysics, solar physics, and exoplanetary and astrophysics. For his PhD, he developed a cutting-edge numerical model to study the solar corona and the solar wind. And then he moved here at the Harvard-Smithsonian Center for Astrophysics, and he reached for the stars. While he kept working for the sun, he used this code to model the stellar coronae and stellar winds. And he has done a number of works as well, implementing sun using models that connect the Earth to the sun to connect for star exoplanetary connections. So he has done significant work on exoplanets as well. Today he will talk to us about a new exciting system, and he will talk about the space environment of TOI 700T.
Okay, can you hear me?
Yes.
So, hello everyone. It's always exciting to get back to the place. I've been here for a number of years. Maybe too much, no. It's nice to come here. After you leave, you realize how great this place is to be a scientist is. Pretty much, you go to the bathroom, you meet somebody on the way, you talk for 2 minutes, and you have an idea for a new paper. That's how great this place is. So it's really great place, and especially as a young scientist, as a postdoc, the opportunities to work with pretty much on any subject. You can find a person here that works on that subject. Typically, that person will be happy to collaborate with anyone who's interested. And the opportunity to expose your work to the world, it's also great here, or greater than other places probably. And again, it's just a great place to be. Today I'm going to talk about a very recent work. It's still kind of work in progress. I hope to finish the paper next week and submit it. There's this new exciting system that was discovered very recently. It's pretty much only published on 3 follow-up archive papers. It's not even formally published in the peer-reviewed journal about the system TOI 700D. It's the first test system that there's a so-called confirmed habitable exoplanets. And what I do for a living, and I still have a very active collaboration with all this role pretty much except for Christine, and that we study the impact of the space environment, the environment between the star and the planet and around the planet, the impact of the space environment on the habitability of planets. And in particular, we focus on short orbit planets that orbit M dwarfs in short orbits. And the main question we ask, if the harsh environment that is expected around these orbits is indeed very harsh, can this planet be habitable? In particular, we try to estimate, can this sustain their atmosphere for a long time? Because the planet is a bird, doesn't have an atmosphere. It's not impossible for it not to be habitable, but it's less likely. And I guess part of the definition of habitability is to define, is that planet very similar or not to the Earth? Which is good and bad, because if we can define that, yes, indeed, we know that Earth sustains a lot of life. Therefore, if we can find a planet like the Earth, there must be life there, right? Or there's a high chance for that. On the other hand, if we focus about only Earth-like things, we pretty much eliminate all the things that may be different. And there must be different ways of life in the universe beyond the Earth. We actually find extremophiles here on the Earth, pretty much living things that live in places that we just did not expect to find life. So that by itself should tell us that we should expect life to be everywhere in the universe the moment we find them in one place. Until then, we don't know if there's life beyond the Earth, but the moment we find one, there must be everywhere. So that's my kind of introduction and philosophy to the thing. Most of this work and most of the work that our team worked on exoplanet research was done under the Living Breathing Planet team. That is a Nexus-funded collaboration that we're part of. This is part of the people I directly work with on this project. So let's start to talk about this star. This star was discovered by TESS, or this planetary stellar system and planetary system was discovered by TESS. The star itself is an M2 M-dwarf star. It's located at 31 parsecs from us, not that close. It's about 0.4 in mass and radius from the sun, so it's smaller. And it's an old star. It is estimated to be older than 1.5 gigayear. And its rotation is very slow. It's about twice slower than the sun, or maybe a bit less than that. So it has a very slow rotation. And that means that in general, and there's also evidence in other indications, that this star is very, very quiet. It's not an active star. It doesn't flare much. It just sits there, does its thing. The star is located, this is the TESS field of view. It's located close to the southern pole of the Kepler field of view. And again, this is the main paper of the discovery of this system. There are two follow-up papers to confirm that help to confirm the planets and get some idea about the habitability of these planets and their atmospheres. This is the planetary system. It composed of three main planets. The TOI 700b, C, and D. B and D, the B and D planets are Earth-size, radius of about 1 Earth radius. TOI C is about twice that size. It's a mini Neptune or a super Earth. This is a picture that shows the habitable or estimated habitable zone of the planet if you just consider the luminosity of the star and the distance of the planet from the star. This is what we call the conservative habitable zone. So it's the habitable zone based on the relatively narrow definition of the habitable zone. And you can see that the planet D resides on the inner most parts of the habitable zone. So planet D is potentially habitable, and this is an Earth-like planet or Earth-sized planet. So it's the first discovery of the TESS survey of an Earth-sized planet that resides in the habitable zone, and that's why it's exciting. So that's the planets. These are other parameters of the planets, their distance from the star. All the orbits are still relatively short. So you can see that the planet D is about at 0.1 AU from the star. Just for reference, Mercury's orbit is about 0.27-ish or so. So it's still much closer to the whole star compared to Mercury, which is the innermost planet in our own solar system. So what our investigation aims to discover or to define is what is the space environment around this planet, TOI 700d, and how does the space environment might impact the habitability of this planet. So this is pretty much the question we try to ask in everything we do, and in particular in this planet. The main thing we try to quantify in our research in terms of impact is a mass loss rate or escape rate from the atmosphere. Because if the escape rate will show that the planet's life is about 1 billion years, and after 200 million years, all the atmosphere is lost, then there's less likely that this planet sustain an atmosphere. So we try to quantify the escape rate. And this is a figure from a recently review paper that our team, the Nexus team, submitted for review for JGR. It's led by Guillaume Grenoff. And it's a review paper of all the known escape processes from planets in the solar system. And just to stress that it includes thermal escape processes, which are commonly considered in the context of exoplanets, but there's a wealth of non-thermal escape processes that are highly known from solar system planets that are typically ignored or not considered in the context of exoplanets. So one of the goals of this review paper is to show that, look, there's all these escape processes that we know about in the solar system. We should look at these escape processes in the context of exoplanets when we try to estimate escape rates from exoplanets. And in a matter of fact, in some situations in our solar system, we know that the non-thermal escape processes are actually the dominant processes over the thermal escape. And again, we try to ask the question, can TOI 700D sustain an atmosphere? And this is a summary of some of the work that was done on this topic by us and some other teams. And indeed, we've seen indications of very high mass loss rates in Proxima Centauri B and TRAPPIST-1 system. These are other systems that have been discovered recently. This is an example of my study that showed that for a Venus-like exoplanet that reside in a close proximity to the star, the escape rate may be increased by four orders of magnitude. So it's a significant escape rate. There's some other work here that was done by Garcia-Sage and Tron-Fei Dong that led to similar conclusions. Cecilia also had some papers about Proxima Centauri B and TRAPPIST-1. So the bottom line is that there's an indication that the escape rate can indeed be very high. There's also indication for a strong Joule heating. It's a heating that occurs at the top of the upper atmosphere of the planet as a result of the interaction with the stellar wind. And that heating can inflate the atmosphere and, again, increase the escape. How we do these simulations? We take advantage of a suite of very sophisticated models that were developed pretty much or mainly for the solar system science and space weather. And the system contains a model around the star to calculate the solution for the stellar corona and stellar wind. And then we take this solution, we extract the information along the orbit of a planet, and we use that extracted information to drive a model around kind of a box around the planet, and that will give us a solution of the planetary magnetosphere all the way down to the ionosphere, the kind of the upper part of the atmosphere. And then we can take that information and in principle propagate it down into the atmosphere. We use the space weather modeling framework, which was developed at the University of Michigan over a large number of years. The idea is that this framework couple different models. Each model is in charge of its own domain, has its own physics, its own time step, its own grid. And these models are coupled together and they talk to each other in a complete real-time manner. So such a system enables us to get much more self-consistent and precise solutions for the overall system. And this is just an example that these models on the left are focused more on the star, its corona, its stellar wind, coronal mass ejection sometimes and stuff like that. And then this information is propagated, and these models on the right are focused around the planet. So we have a model for the magnetosphere, radiation belt, the upper atmosphere, and all the physics that is concerning the planet. So we take advantage of this system to do our exoplanet studies. And we also relied on the fact that this system has been vastly validated against solar system data, which is something that we don't really have enough information in the context of exoplanets and stars. The data is very sparse. Here we have a lot of data, so this has been vastly validated that it's working. In order to drive the stellar corona and stellar wind model, which is pretty much the driver of the whole thing, we need information about the stellar magnetic field on the surface. Unfortunately for this particular star, we don't have such information, but we do have a very limited data of some of that kind for other stars. So we look for the star that is most similar to TOI 700 that does have information about the magnetic field. And this star was CE-BU. You can see the comparison of the parameters. They're both M2 stars, similar masses and radius. The main difference is the age and the rotation period. So CE-BU is a much younger and more active star, which will have an effect on the magnetic field on the surface that we think TOI 700 will have. So what we did two runs because we have the model. We can just tweak the parameter. So we use this magnetogram or magnetogram input as is. But we also have another run that we scale this down to about 10% of the magnitude. So instead of about 300 Gauss maximum field, we have about 30 or 40 Gauss field. And so we had two cases that we looked at. One is a weak field and one is a strong cell field, just to have reference options about what could be possible impact on the system. This slide shows the solution projected on the equatorial plane. The black lines represent the orbits of the three planets in the system. The contours show the dynamic pressure of the stellar wind normalized to a typical dynamic pressure here on the Earth at 1 AU. Okay? And you can see that this is the strong field case. You can see that the dynamic pressure is much, much higher than 1 AU, between 100 and 1,000 times more. But if we look at the scaled-down magnetogram solution, you can see that the dynamic pressure is maybe 10 to 50 times higher. It's still higher than the Earth, but not extremely high. This is one of the things we want to show. The field lines just show the magnetic field lines. These are the extracted parameters along the orbit of TOI 700d, which is the planet of interest. It's the outermost planet of all three. I show here the plasma density, velocity, magnetic field, and the Alfvénic Mach number, which is the ratio of the velocity of the wind to the local Alfvén speed. And you can see that it's mostly super Alfvénic. So this is similar to the Earth. The solar wind of the Earth is almost all the time super Alfvénic. So this is the case of the strong field. You can see that the density, for example, it's very large. Just for reference, the density of the Earth, typical density is about 5 cubic centimeters. Here we're talking about a few hundreds. It's much higher density. Magnetic field also is about 10. So here the magnetic field is much larger for the strong field case. But if we look at the scaled down case, now we're getting much closer to a typical parameter at 1 AU. You can see that the 10 Gauss, this is nanotesla. 10 nanotesla typical value at the Earth. Here is slightly higher, but not ridiculously higher. Same with the density. The velocity is similar to a typical solar wind speed at the Earth. So the scaled down parameters are not that extreme anymore. Comparing to what we had. We use these parameters to drive a model for the magnetosphere of this planet. We assume that the planet can have different planetary field values ranging from 0.3 Gauss, which is the Earth's field, to 1 Gauss and 4 Gauss, which is Jupiter's field. So we have a ranging of potential planetary field because we don't really know what the magnetic field of this planet is. We don't know what any magnetic field of any exoplanet is. We have zero information about that. So we can just scale solar system options and say, okay, let's look at the ranges between them. The top two rows are for the weak field case. So you can see the density is much lower. The contours are of density or number density. You can see the density is much lower. The magnetosphere is not that compressed. It looks pretty much like the Earth, depending on the planetary field that pushes against the solar wind or the stellar wind. Here in the case where the density and the magnetic field of the stellar wind are much stronger, you can see the magnetosphere that is shown this white line that's a bit hard to see. The magnetosphere is much more compressed. And that may impact the atmosphere of the planet. These two are reference cases from the Earth. So this is the case of the Earth with ambient solar wind conditions. And this is for a strong coronal mass ejection conditions. So this is just give you a reference. They're the same in the two panels or the two cases. It just give you a reference of these solutions, comparing to different. The last thing I did is I took this input and I used this input to calculate the Joule heating of the upper atmosphere of the Earth. The Joule heating occurs because we have the Earth's magnetic field. The field lines go down to the upper atmosphere or the top of the upper atmosphere, and they close down. So there are currents that's flowing along these field lines. These are field line currents. And these currents needs to be closed down somewhere at some layer of the atmosphere. That layer is the ionosphere, which is conducting enough to close on the current. So we have these conducting layers that these currents are closed down at that layer. But because this is a dissipative layer, we should have Joule, or we may have Joule heating, which is the resistive dissipation of heat as a result of these currents. So we have the tool in this model to calculate this Joule heating. And what I show here is this is the weak field case and strong field case. This is the x-axis show the planetary field magnitude, and on the y-axis I show the integrated power of the Joule heating. And these two red dots also, again, show the reference case for the Earth. This is the Joule heating during the ambient solar wind conditions, and the other dot shows the case of a strong coronal mass ejection event or geomagnetic event. This is the weak field. You can see that the heating is not that large. It's less than what we have on the Earth during a geomagnetic storm. But for the strong case, you can see that the ambient heating, just due to the ambient stellar wind as the planet orbits the star around, can be quite large. And again, Joule heating can inflate the atmosphere and drive some higher escape rate. That's why we care about this heating. So this is the results. Just to summarize the question, can this planet sustain its atmosphere? The answer is perhaps, but depending on the detailed parameters, and this is where we still have some uncertainty. So we need to have a better information about the stellar magnetic field. So hopefully we'll have some observation there. It's going to be challenging because of the very slow rotation of the star, which makes it nearly impossible to make these Zeeman Doppler imaging observations of the magnetic field. We need to know something about the planetary field. Again, very unlikely in the near future to know anything about that. We need to know something about the atmospheric composition. That can also play a role in the escape. And the stellar radiation, of course, can also play a role. And will we get some information from JWST? Probably less likely, because the chance of getting it for an Earth-like planet is probably not large. We're probably going to make some attempts, but most of the atmospheric information we're going to get is going to be from hot Jupiters and larger planets. And just to wrap up, we're currently working on the next step of our collaborative effort. We submitted a proposal to the ICAR program, which is the continuation of the Astrobiology Institute program, where the idea is to create a coupling between the different models that I showed you, but this coupling now will going to be much more self-consistent, time-dependent, and physics-based manner. So everything is going to be much more physics-based in general. That includes model for the atmosphere that accounts for non-hydrostatic grid or geometry, the full chemistry of the atmosphere, composition, thermodynamic, 3D dynamics, which makes a huge difference from 1D dynamic that we see, and also maybe planetary magnetic fields. So again, we aim for this more self-consistent, or the development of more self-consistent system that will enable us to pretty much study, perform studies star to clouds of any exoplanet that we have some sparse data about. So that's kind of exciting to be able to do that in the future, or it will be exciting. So that's where I stop. Thank you.
You use the Earth's magnetic field as your minimum, but I thought Mars had even less, or zero. Was there a reason not to consider even lower planetary magnetic fields?
Well, we did do simulations in the past of non-magnetized planets. Here we just choose to, in this initial study, to do an Earth-like magnetized planet. But we did in the past non-magnetized planets. We can pretty much take the Mars model and just move it close. So you increase the UV radiation, and you use this stellar wind input in the same manner, and you hope that the model won't crash with these conditions, and that you should be able to do some stuff. Mars has extremely complicated interaction with the solar wind. It is magnetized in some places, and it's non-magnetized in most other places. It has a direct interaction of the solar wind with with the atmosphere, which leads to a lot of ion chemistry involved. These models are very, very complicated. But you could do it in principle.
Yes.
What's known about the atmosphere in this TOI 1700?
They had one initial study in this series of 3 papers that they used pretty much Earth atmosphere models to do some calculations about the
Is there direct detection of an atmosphere?
No, nothing like that yet. And I think, again, I'm not an expert on this kind of observation, but as far as I know, these are extremely challenging observation to do for an Earth-sized planet, comparing to hot Jupiters, for example, which you can really get spectral observations.
So one of the biggest things that we're trying to figure out with TOI 700D is how massive it is, and therefore what is the actual composition. What influence does that have if the composition of this planet drastically changes on your results here?
Well, here we don't really include the atmosphere, but in our next stage of this kind of work, we plan to use an actual model for the atmosphere, and that's where the composition can have a huge impact on the whole interaction, because it will be all down to the chemistry and the interaction of the chemistries. A lot of the escape, I didn't mention it, but a lot of the escape eventually shows up in the form of ion escape, not neutral escape. And the ion composition depends on the composition from below, so it will have a dramatic effect. And we would like to try to develop tools that will enable us to just look, okay, let's try this, let's try that, and see what happens.
With so many planets reasonably close, how stable is the whole system?
I don't know. It's plain and simple.
Any more questions for Ofer?
Has Tess observed any flares from this system?
No, so this star is considered to be extremely quiet as far as I know.
But this is in the CVZ? Your first slide showed where this, near the, you said it's near
Yeah, I
the
think so. I think they explicitly mentioned it's a very quiet star.
No, I'm just wondering how much coverage there is on that.
Again, I'm not sure.
Okay.
There's a whole floor here of people that should know it.
We're all sitting back here.
So it's in the continuum zone, right?
It's near it. It got 11 of the 13 sectors because it landed on one of the chip gaps.
So you consider your strong field case and your weak field case, which may roughly correspond to, say, present day stellar activity and earlier in its lifetime. And you showed how they sort of correlated with typical Earth conditions and those during a CME. What about flaring when it was younger, and what effect do you think that may have on the atmosphere? So if there were a lot of flares when it was younger.
So that's a great question. So what we did so far in this kind of project was to pretty much take a snapshot of the system and the planet and try to maximize the information using this suite of models. The next step we plan to do is to look at the evolution of everything with the stellar life or the planetary life. For example, you asked, can this planet sustain an atmosphere? You can also ask, how come this planet develop an atmosphere in the first place if it resides very close, right? So there's all these evolutionary things that are very valid to investigate, and we plan to do that. It's on our plate.
All right, let's thank Ofer.
So our second speaker today is Mackenzie Jones. She's a postdoc here at CFA, so possibly familiar to many of you. Mackenzie got her bachelor's from Butler University in Indiana, and then she got her PhD from Dartmouth College, where she was working with Ryan Hiscox, mostly on developing simulations to study the cosmic evolution of supermassive black holes, and to really understand the importance of selection effects in observational studies of supermassive black holes. So she's been a postdoc here at CFA since 2018, She's gotten her hands more on data, X-ray data in particular, and she's been working both on detailed studies of nearby galaxies as well as large statistical samples at higher redshift. So today she's going to be telling us about one of these nearby AGN, about NGC 7212, large-scale extended hard X-ray emission.
Thank you. So this is my third time at this podium. The first time was about 10 years ago when I was an REU student. And so this is very familiar to me. So I'm very happy to be here to talk to you about the work that I've been doing on NGC 7212, looking for extended hard X-ray emission. So my talk's broken into 3 parts. The first of which talks about NGC 7212 and how it fits into our understanding of the AGN unified model, because it's slightly out of place, and so I'll get into that a little bit. Then I'll be telling you how we actually measure the extent of this emission by fitting radio profiles of the extraction regions, which I'll get into. And finally, I'll tell you about the spectral fitting, so how we actually try to understand what this emission is, not only where it is. So NGC 7212 is joining a sample of other nearby Compton-thick sources. A lot of these sources are in normal Seyfert Type 2 galaxies as classified by their optical emission lines, with bright O3 5007 cores and no history of nuclear starbursts. They've been found to have extended emission on hundreds of parsecs to kiloparsec scales, specifically in the soft X-rays, and only until recently have we been able to see extended emission in the hard X-rays as well. The ones indicated in our blue are the ones that our research group here has been studying in particular. The most comparable of these is ESO 428, and so I'm going to be referencing back to this source quite a bit in this talk. It has exhibited complex spectra and extended emission on kiloparsec scales, both in the soft and the hard X-rays. So when we observe these sources with extended hard X-ray emission on these scales, this actually challenges our understanding of the AGN unified model and where these hard X-rays are originating. So getting into the AGN unified model, this is a very nice cartoon of what we consider the AGN unified model to be in fairly simplistic terms, which I know this is a lot, doesn't look simplistic, but it is. We have the supermassive black hole in the center, surrounded by some sort of accretion disk. Outside of this disk is a dusty torus that can obscure the radiation along this plane. And if we observe a source through this torus, what we see is an obscured source, or a type 2. Through the opening angle of the torus, we have our ionization cone, and if you're observing the source through that ionization cone, that's where you see your type 1 or unobscured sources. So the hard X-ray continuum and this fluorescent iron K alpha, which is seen in many X-ray observations, is thought to be originating from the interior parsecs due to the excitation of the obscuration material, so this torus. However, for Compton-thick AGN, this torus has column densities of 10 to the 23, 10 to the 24, etc. And so this acts more like a screen, completely blocking all of the radiation in this planar region. So the question is, how can an AGN be both Compton-thick, where the radiation can't escape, and also have extended emission both along the ionization cone and in this cross-cone region going through the torus? Well, recent work suggests that the torus is not actually as homogeneous as we think. It's not a solid screen. It's actually likely clumpy with lots of gas clouds. So it allows for reflection and transmission as it escapes through these clouds. And a good representation of this is shown here in Buchner's UX clumpy visualization. And so in this scenario, it's possible to have hard X-rays leaking through a Compton-thick torus because of these clouds. So when we look at these nearby Compton-thick sources with high resolution and a large number of counts, these are actually a great environment for finding this extended emission so that we can better understand the limitations of the unified model and gives us clues to how AGN can impact their host galaxies via feedback mechanisms. So moving on to the part that's more of what I did, this is NGC 7212, which is a nearby Compton-thick galaxy, or Compton-thick AGN, and an interacting group of galaxies. So here is the galaxy in question. This is one of the group members, and then there's another one that's like all the way down here. So previous observations of NGC 7212 have been done in a variety of multi-wavelengths. So in the optical, it's been observed to have diffuse, extended, narrow line emission on kiloparsec scales, polarized optical broad line emission, and this is generally in line with this region here. In the radio, it's been found to have a compact to double radio source with an extent of about 0.7 arc seconds, and moderate radio power aligned with this extended narrow line region. In the X-rays, it has been observed before, and it's been shown to be non-variable with complex spectra and also Compton thick. But we observed it with a cumulative Chandra exposure of about 150 kiloseconds. So this is a zoom in on the previous slide. So the following images I'll be showing you are 1/8 subpixel data that has been adaptively smoothed, where the adaptively smoothed parameters that we've selected were chosen to optimize the details of the extended diffuse emission. This is the axis aligned with the radio source. The interior circle indicated is 1.5 arc seconds radius, which corresponds to about 0.8 kiloparsecs. And the exterior circle is an 8 arc second radius, which corresponds to about 4.5 kiloparsecs. So even just visually, we can see that there's some interesting X-ray extent here. So what we did was we split this, so right now this is the 0.3 to 7 keV, into bins of energy. And we started with the soft X-ray, the 0.3 to 1.5 and the 1.5 to 3. And you can just see visually, this is only a visual classification, that we see kind of diffuse extended emission that kind of hits the outside of this 8 arc second circle. But we can go further and look at the hard X-rays. So if we do 3 to 4, 4 to 5, and 5 to 6, you still see this diffuse kind of wonky emission. There's no azimuthal dependence or preference in this case, but the extent starts to decrease, which is kind of what you expect. The harder X-rays we know we believe originate in the interior, so we don't expect them to be completely outside of the galaxy. But what's interesting is if we continue on and look at the 6.1 to 6.5 arc second region, where we would expect to see iron K alpha and zoom into it, we actually see extended emission that visually you can classify as about 3.8 kiloparsecs. But this is just completely qualitative. This is just looking at the images, which are pretty, but don't really tell us much about what's going on. So what we did next was a quantitative measurement of this extent. And to do that, we, for each energy bin, extracted the radial profile in 2 separate regions. The regions were selected based on an azimuthal projection of the surface brightness. So we have the south-north region here, which is aligned with the radial lobes and encompasses the extended narrow line emission, and an east-west region, which is where we would expect the cross cone to be, where the impact of the torus is going to have, where the torus is going to have the most impact on the observed emission that we see. We also modeled the Chandra PSF and normalized it to the central 1 arc second so we can compare how many counts over the Chandra PSF we would expect for this source. So when we do this, in the 0.3 to 7 keV, our Chandra PSF is in black, and the excess points in the south-north region are in red. And I colored it to make it a little bit easier to see what the excess is in this particular case. But we find 570 counts over the Chandra PSF, which is pretty significant. In the harder X-rays, 3 to 6, we find 89 counts. And then zooming into where we expect this iron line to be, we find 11 counts, which is still significant, although 11 counts is not, granted, very much. But because this is the south-north cone that encompasses the extended narrow line emission, we would expect there to be quite a few counts in this compared to the other regions. So we can actually separate it and see what the radial profiles of those regions are as well. So looking in the west-east cross-cone region, keeping in mind this is where we expect a lot of the emission to be obscured by this torus, we find 242 counts over the Chandra PSF, which is still fairly significant for the 0.3 to 7 keV range. Zooming into the hard X-rays, we find 39 counts, still significant. So we have hard X-rays that are significant outside where we would expect this torus to be blocking it. Zooming into the iron, we only find 4 counts. So it's not quite significant, but when you combine all of the hard X-rays together, it then becomes more significant. But it's interesting just to look at the iron line in particular because we wouldn't expect to see this out of the central region. So just visually, you can kind of see, oh yes, there's less counts in this one compared to the other, but what's most useful is to actually give a fit to these radial profiles. So what we did was we fit the radial profiles with a spline approximation and calculated the full width half max. And what we found is that the full width half max basically just probes the inner nuclear region because it is so bright in the inner nucleus. And there's not much difference between the south-north and the west-east extraction regions. So what we did instead was looked at where 1% of the surface brightness is for this object on these radial profiles, because that will tell us more about what the extended emission looks like. When we do this, we find a fairly significant difference between the south-north cone and the west-east cone. But what's interesting is we're still getting transmission in this cross-cone, this blue region right here, despite the fact that that's where the torus should be. So we actually did a quick estimate of how much transmission we're actually seeing using a back-of-the-envelope calculation. And we find that the transmission in the cross-cone region is about 15% the emission in the cone region. And if we compare this back to ESO 428, which I told you was the closest companion to this, ESO 428 has a transmission of about 10%. So this is a fairly high transmission, and that might also be due to the fact that it's more blobby in shape, where ESO 428 was elongated, as we saw. So we've quantified the extent, but we don't know much about what this extent is. What is this emission actually comprised of? So we looked at the spectra. For this, we took 3 extraction regions, the 8 arcsecond circular region, which remember is about 4.5 kiloparsecs, looks closer in, specifically at the nuclear region, where the Compton-Thick AGN should have the most power, and then in the 1.5 to 8 arcsecond annular region. So that's really probing this diffuse emission that we care about. So I'm going to start with the nuclear region. We'll come back to the circular region at the end. So this is the spectra, and it looks pretty good for having, the number of counts we had, which was about 1,200 in total. So the first thing that we did was fit the continuum with an absorption and PEXRAV component. And if you're curious about the different PEXRAV tiny little parameters that I used, feel free to ask me. I have them all written down and in my head because I just submitted this paper again. So what we did was we took this base continuum and then started to add emission lines until we had non-significant detections, and we minimized the residual. And so what we find is that in the soft X-ray region, we find blended emission that's typically observed in nearby AGN, which is great. This is what we wanted to see. So we have neon 9, magnesium 11 and 12, silicon, and then a bunch of different species of iron. But you'll notice that's not the only emission lines in this. So if we move on to the harder X-rays, we find also typical emission observed in nearby AGN. So we have some sulfur K-alpha, iron K-alpha, which is just this booming structure here. And so that's pretty typical. You'll notice we haven't seen all of the emission lines yet, and this is where it gets pretty exciting. We find hard X-ray emission that is not typical of AGN emission lines, located here between 3 to 5 keV. So these are all tentative identifications at this point because we don't have too much to compare to. But we think they're probably species of argon and calcium. And I can get into a little bit more of why that is, and I will in a second. But you'll notice I've skipped one line right here. There's emission at 5.2 keV, which is just completely puzzling to us. So we have this non-typical emission line, and it's a more than 3 sigma detection. We've ruled out a contaminating galaxy. There's no obvious problem with the ACES background at this point, and no obvious line species associated with it. Up until a couple days ago, we had no clue what this is. But we found a possible explanation in the form of cosmic ray spallation. And for those of you who have no idea what that is or heard it, 20 years ago in your textbook, cosmic ray spallation is this nuclear spallation where a light projectile such as a proton or a neutron or some other light particle with an energy of mega electron volts to giga electron volts hits a nucleus such as iron, and this leads to this large fragmentation of the iron molecule into hadrons or other fragments. And this is where you can actually get these larger, heavier, weird elements you wouldn't expect to see. So the importance of this spallation in AGN is completely debatable, as is the origin of these energetic particles. So the newest, or the first kind of discussion of spallation in these nuclear sources came from Skibo 1997, in which the spallation is originating in the interior galactic center. And so his idea was that the bombardment of accreted material with high energy protons causes this spallation of heavier elements, which actually alters the composition of the accreting material, which is interesting. More recently, another explanation was offered by Turner and Miller in 2010, where the spallation actually doesn't occur directly in the center, it can occur in a disk wind. And in this wind, since it's a thinner target, your energetic particle doesn't have to be quite so energetic, and you only need a moderately relativistic particle, and so it might be a little bit easier for spallation to occur. And it's also, interestingly enough, then subject to the outflow velocities that might be detected with a future calorimeter. So another calorimeter, keep that in mind. We need one of those. So this is an example of the Gallo 2019 spallation simulation of a variety of heavy things, such as titanium, vanadium, chromium, manganese, etc. But you'll notice I've marked one in particular with a giant arrow. That is vanadium, helium-like, and it is at 5.18 keV. Who knows? This could be it. But vanadium, in comparison, is typically weak, so it's unclear if this is actually a really good explanation, but this is the closest we have so far, and I am willing to take more suggestions if you have them. So moving on, we might have this line, but we also, instead of just doing the individual lines, looked at a physical spectral model for NGC 7212 in this internuclear region. So for this, we actually started with a photoionization model and then kept adding photoionization models to see if we could figure out what's going on. That didn't work. So then we took thermal models and took a single thermal model and added single thermal models to see if we could best fit this spectra, which also didn't work very well. So then we started mixing them together because we knew in advance that this was going to be a complex spectra. So we started just kind of picking one and then the other and adding them all together until what we found is that the best fit for the nuclear region was a single photoionization model and a single thermal model together. But two photoionization models were preferred. So when we moved to the annular region, we started again with these Gaussian emission line fits. Similarly, we found in the soft X-ray things that were consistent with a typical AGN. Still have our neon 9 and our magnesium and silicon. The hard X-rays still had that iron K alpha line, even though at this point we're almost to 1 kiloparsec out. We have significant identifications, although less significant than in the nuclear region, for these weird argon-calcium lines. But we don't find significant emission at 5.2 keV. So it's really limited to this inner region, and so it's going to be a very interesting thing. We need some grading spectra and things like that, some more high-resolution things to actually parse out what's going on. The photoionization models and thermal model combination that we need for the annular region, so this diffuse emission, was best fit by a single photoionization and single thermal combination, but two thermal models were preferred. So it's kind of the opposite of what we saw in the nuclear region. Putting this all together, if we now go to the 8 arcsecond region, we would expect things to kind of add together correctly at this point. So we'd get a little bit of one and a little bit of other since we have the two regions and we're just combining them. And what we find is that, indeed, when we fit Gaussian emission lines, we get emission lines that are consistent with what we find in the first two, as well as with typical AGN. looking at the physical models, this is where it gets a little interesting. Our best fit models for this were 2 photoionization models and 2 thermal models. So it's a combination of the nuclear and annular physical spectral models. So we did some more analysis on the thermal parameters, the photoionization parameters, to try to figure out what was going on here. So, looking at the thermal models in particular, we found that they were equally well explained by shocks, jet ISM interactions, and supernova. So we couldn't rule anything out, but it's consistent with all of them. And then, so for example, I'll just do a quick example because I have a little bit of time. In the 1.5 arc second nuclear region, we found a thermal component of 0.8 keV, which is very consistent with what's been observed before for this source and in other Compton-thick AGN. So this would have shock velocities of about 850 kilometers per second, which corresponds to a supernova rate of about 0.1 per year. Seems reasonable. In the 1.5 to 8 arc second annulus, we find this lower temperature component again, but we also find a high temperature component of about 6.8 keV. So this would correspond to shocks of about 2,400 kilometers per second. And shocks or velocities at this speed are actually consistent with what we see and what we would expect from O3 velocities that have already been observed for Compton-thick AGN on extended scales and can be associated with starburst-driven winds. So there's lots of really interesting things going on in here, and it would be great to kind of distinguish between them, but we're not there yet. So in summary, we observed extended X-ray emission for NGC 7212. In the soft X-rays, it was about 3.87 kiloparsecs at 1% of the surface brightness. And most importantly, in the hard X-rays, up to 2.7 kiloparsecs, so just this booming hard X-ray emission. In comparison with ESO 428 at 1% of the surface brightness, the extent in the soft emission is about 3.4, and in the hard is about 2.7. So it's very comparable to what we're seeing. This extended emission may be related to the compact double radio source. There's been a bunch of simulations that can explain the type of thermal emission we're seeing, but I won't get into that. If you have more questions, feel free to ask me about it later. We observed extended emission in the cone and the cross-cone region, most importantly in the cross-cone region because that's where the torus should be blocking most of the radiation that we would see. And so this has implications for the torus model and the unified model of AGN. We find 3 emission lines that are not consistent with typical AGN observations around 2.9, 3.6, and 5.2 keV. And they're possibly fluorescent species of calcium, argon, and vanadium, of all things. But we're really going to be looking into that in more depth later on. Also taking suggestions. And then finally, NGC 7212 requires a complex combination of photoionization and thermal spectral models. So this is indicating that there's some type of complex gas interactions going on. But this is consistent with what we find in other sources like ESO 428, although it's less complex than these other sources. So I've hopefully convinced you that this work demonstrates the advantages of deep Chandra observations for recovering statistically significant spatial and spectral information. So this is a really exciting class of Compton-thick AGN with diffuse hard X-ray emission on kiloparsec scales, which is just astounding. So high-resolution observations of these sources are really important because they can recover information about the AGN and the ISM, test the AGN standard model, analyze the morphology of the torus, and give us new insights onto gas dynamics and AGN feedback mechanisms. So as we plan for the next generation of space observatories, such as LINX, we really need to emphasize these high spatial resolution and sensitive instruments because they will play a crucial role in the future of AGN studies. Thank you.
Questions from Mackenzie?
I answered all your questions.
You said there is a binary in the middle. But what is the orientation? Do we know anything about it?
The radio source, you mean?
Yeah.
Yep. The radio source is oriented along this line here. And so it's also oriented along, so this is actually a zoom in, so this is only 2 arc seconds across right here of the inner region. And so the radio source is aligned here, which is also where we see the extended narrow line region. It lines up with that.
What did you mention, 0.7 arc seconds?
The extent of the radio, the compact double radio source is
Right,
is
and it's in that
0.7.
direction.
It is in that direction.
So do you see this 5.2 kV line also in the ESO source?
So no, at least not with any significance by eye. So that's something we're going to be looking at in addition to a couple other sources that Martin and Pepe have to actually delve into that a little bit more. We do see it when we stack the Cosmos spectra, though, which you know. And so we know it's not just in this source. We're seeing it elsewhere.
Have you thought about it possibly being some sort of escape peak from some lumpy stuff? All these, whatever you want to call them, things in the torus that are not just dust, but maybe bigger things.
Right, so that gets into a little bit of the spallation. Like if the spallation is from disk winds or if there's some sort of wind going on, maybe there's something associated with that, but I haven't really thought about the clumpiness of something escaping exactly. I'm not sure we have the resolution to actually figure that out at this point.
If you go back to the slot, please. I thought that when you consider these high energy protons that are just hitting the iron, there are other peaks as well. So do you have any explanation why the others don't show up? Or?
No, and that's one of the caveats is that it's vanadium in this particular simulation is so much weaker that we should, if this is going on and those things are occurring, we should see that. Since this is a simulation, there are caveats in the simulation that if there's any orientation effects, if there's if there's any deviation from exact, if the metallicity is different, there's a bunch of different things. If it's not actually iron you're hitting and it's a different type of thing, it can change this. But it was pretty exciting that we saw something similar to what we were seeing after looking at this for a very long time.
Maybe you already said it when I lost it, but which atomic databases did you use for the spectral analysis?
For the spectral analysis, I used the NIST Atomic Spectral Database, as well as people in this room who are much more knowledgeable about atomic databases than I, and also referenced a lot of papers that have been of nearby components like AGN to see what spectral lines they have and do a comparison that way. So it was kind of a very broad search. And vanadium, interestingly enough, does show up in the NIST database, but it doesn't show this particular flavor. And so that's not something that appeared on our radar.
Final question? If not, let's thank Mackenzie again.
For because actually has been integrating. The point is that if you see the vanadium 5.1, you should see also the forward.
Yes.
The 5.4, so it makes sense.
Shall we go? Radiate concrete combination. Because in photo ionization system, I can actually check on some of those because I follow 6 readings, so Ofer A, and definitely seems to strong ROC. That one that's a 5.2 may be a constant, but I don't know. But the ones for self-resistance, especially self-resistance, are very prominent, and then we seem to actually great. But I can send you, I'll check, I'll send you a link to the paper, and I'll also check. If we have a table of ROCs, we can directly, if it is an ROC, directly be sampling the temperature of the
Yes. Okay. Yeah, I know we're going to be proposing for gradient vector, because it's still a little fuzzy, but definitely.
Okay, I'll look at it and send it to you, because like I say, it's a possibility.
Okay. Yeah.
Because, as I say, we can get to highly photonized, in the case of C6, it's even more complicated in that, because we're getting, most of the lines are there hydrogen and helium. We see them all the way from iron down to magnesium. So we're seeing calcium, argon, sulfur, silicon.
For this semester, we're
so is there,
although
the fact that
several of us are releasing in the fall, and so it would be really helpful actually.
Well, I mean, that's the thing, with some of the RCs, I'm not sure of all the conditions necessary, because we see them come and go in different states. So maybe a specific state. Also in CX3, there's a complication in the spectrum we see. You cannot produce one single photoionizing source, because to produce the iron lines is you need something with an ionization parameter of 4 to 5, whereas the sulfur and silicon lines are 2 to 3. So there's a completely different, and not only that, there's evidence that the iron tends to follow the compact opposite, which you sort of expect. And in the sulfur and silicon, you actually find, look really to be following the shadow. But it can't, the shadow itself, it has to be an ionization source, because there's a paper I with Tim Coleman. And Tim actually calculated in the transition going into the shadow, the things like silicon and sulfur would completely become neutral within about 30 seconds.
We definitely try to get,
And so to see them and see the hydrogen helium, like there has to be some other ionization. We never came up with a good answer, but maybe something like a Bioshock creating a degree of ionization at a lower level. But I'll send you a link to that and I'll check just to see, because I think in a table and I think we have the energies. But like I say, the 5.2 is possibly calcium, but I'm not sure.
Okay, yeah, and that's why, like, in the lower energies, we were thinking calcium or argon, but if it's calcium, that might make sense because there's inhibitors.
And RC, if you get enough photons, that there's this beautiful whip.
Okay.
And people mistake them, in fact, in fitting CCD spectrum, people fit, and they actually, because a couple of RCs and lines, like a CX3, they'll get this big absorption feature and some absorption feature. It's a set of emission lines and RCs that are bright in other areas and make it appear as a dip.
On YouTube. So there is a person
so for this in particular,
who helps us out with that.
we have a kind of a dip that's after the 5.2.
Yeah, and there actually can be, in fact, I'll send you the links. One of the links I'll send you is actually a poster of mine, because in the paper, Tim likes to use things in times per kV, but I've also sent like photons, made it to a photon spectra, and so the features really stand out.
Okay, yeah, that would be great.
And that will give you something to look at compare for photoionization, because it is a very, but I can also, like I say, send you a link to the paper. I'll check it too, because I think we have a table with RCs in there, and so that's a quick check to see. That's what comes to mind when I think photoionization. In CX3, this is what Mike Noah pointed out too, is Norbert Scholl was pointing these out to them. These are RCs, but once you get enough photons in the gradient, you can really see them, because they form this little lip, and this lip is actually an exponential with the temperature, and so that's a direct measure of the temperature of the gas on the composition.
Thank you. Hi,
hey,
how are you?
Fine, thanks. Sorry to come in, well into your talk. Eileen had an MRI today, so I had to go with her and take the baby. But yes, what I saw was cool, and also the high energy lines are kind of a neat result. And I was going to ask you before you said it, but are you interested in applying for grading data?
Yes, I am.
Yes, cool.
Definitely. I have no idea what I'm doing.
Well, if there's any way I can help out, I'm going to have my hands full with a bunch of things, but I can pitch in.
This is, I guess, 2 weeks from now.
To start within the next 2 weeks.
Yeah.
Put together a base layer.
Yeah.
And
I'll
then
try to
maybe send
remember,
you
I'll put
that
something in my
folder
calendar, and
how to
I'll
figure
email you
out.
before, and
So-
otherwise if you remember, and I
So,
haven't heard from me, you can email me, and
with the NUC
remind
339
each other.
our costs had already reduced and published those,
Yeah.
but you hadn't done the analysis. So, the lack of RRCs was something that was really convincing to John Raymond that what we were seeing was collisional and not photosynthetic.
Nice, so that would be a good thing to check that.
Yeah, if you can't discern between different models using CCD data, that could be a big help.
Yeah, and it's very, very.
Comments or